So the next thing we discuss is the concept of an expectation of a random variable. And the expectation can most simply be thought of as an average. Okay, so you're familiar with the idea of taking a bunch of numbers, you add them up and you divide by the number of them. That's a sample mean. Think of the expected value as, if you like, the mean of the random variable. And in this case, we don't have data, we don't have observations. What we do have is the distribution. So the expected value of a random variable of x, which I'm going to write as e of x, is computed by the expected value of x. We take a sum over all values in the sample space. And now we multiply each possible value by the probability the random variable takes that value. So for each element in the sample space, each one in turn, we substitute in here the value multiplied by the probability of taking that value, and we add them all up in a list, and that gives us the expected value of x. And I'm going to write this, which is often used as mu, just for shorthand, if you like, for the expected value of x, which we can use in future. Makes it a bit simpler in writing it down. So let's do a little example where we work this one out. So let's have a case where x can take the values 1, 2, and 4, and each of these has an associated probability, which again I'm going to suppose is a half, a quarter, and a quarter. Okay, so we could just pause at this moment and verify the conditions are satisfied. That is to say, the probabilities are all non-negative, that's okay, and if we add those up, we get the value 1, so that's okay. So we have a valid random variable and probability space. Okay, so when we've written these two columns down, it's very easy now to write a third column, which is simply the product of the first two columns. So this is a bit like what you might have in a spreadsheet, where you simply multiply one column by another. So we simply take the product, as it says in the formula, of x times its probability. So 1 times a half is a half, 2 times a quarter is also a half, and 4 times a quarter is 1. And then the final thing we need to do in order to get the expected value is simply to add up these three terms, and so we get the value 2. So the expected value of x in this case, let's put down mu, the expected value of x is equal to 2. Okay, well, this particular example, the expected value actually is a member of the sample space. Okay, so 2 is the expected value, and it's also a possible value that one of the random variable outcomes can take. It doesn't have to be that way. So it is possible that the expected value could never occur. And this is where you get phrases like the expected number of children in a household is 1.8, for example. You're never going to get any household with exactly 1.8 children in there, but nevertheless, it's the definition that's used for lots of purposes that results in that, and we kind of live with that as a slightly odd phrase. I mean, statisticians often get teased, if you like, of having 2.2 children, because this is what they kind of have in the expected value. Okay, so we're now going to generalize this statement to a more general function. So a generalization of this is to consider not just the expected value of x, but to consider a function of x, and to take the expected value of that function of x. And this we can compute. The summation is exactly the same. All we do now, you can sort of maybe guess a little bit what's coming. It's not quite predictable. is to substitute in place of x, we substitute g of x, and we still multiply by the same thing, probability x equals x. So this g can be pretty much any function you like. It can be a degenerate function, such as g of x equals 1, or it could be the identity function, g of x equals x, in which case we get back to where we started, or something else you might want. So this g is a very general function, and you might just want to verify special cases. So for example, if g of x equals x, then we end up with, sorry, a capital X here. G of x equals x. We just substitute that in here. We end up exactly where we started in this case. Another thing we might do is to put g of x equals 1. And this will lead to maybe a quite predictable statement that the expected value of 1 equals the sum of the probabilities, or 1 times the probabilities, which we know is equal to 1. So that there is, if you like, you may think, well, that's a vacuous statement. We've just said the expected value of 1 is 1, but that's actually a more general point to make, is that when this thing is deterministic, which of course 1 is, it's always 1, then the expected value of a deterministic value, quantity is just the quantity itself. So that kind of fits in with what we'd like it to be. Okay, so that's the concept of an expected value, and this leads us to define another quantity, which is the variance of a random variable. Okay, so the variance of x which we're going to write as var of x, is a special case of g. So the variance of x is going to be the expected value of, g in this case is x minus mu squared. Okay, so mu, remember, is a symbol we used for the expected value of x, and the variance of x is the expected squared difference between the random variable and its expected value. So this is just another g. This thing here, we can think of that as a general function g, and using our definition, which I've just rubbed off, we could actually write down what that is. So how we would compute it, we sum over values in the sample space, as before, and then we substitute g, so with a lowercase x now for the specific values, and multiply that by the probabilities. Okay, so that's the way we could work out what the variance of x is. And that's perhaps a slightly messy formula, and it's just worth noting a simplification for that, which also shows some of the techniques that are used later on. So this we can simplify to, just by squaring out this bracket, x squared minus 2 mu x plus mu squared times the probability x equals x. And again, separating out the different bits, we have x squared times the probability x equals x minus 2 mu sum x times the probability x equals x. All of these over the same index. And the last one is just plus mu squared times the sum probability x equals x. And you'll notice in that last line there, I've brought out constants in front of the summation sign. So mu doesn't depend on the index that we're summing over. And so I've taken it to the front of the summation sign. X is part of the index, so that has to remain on the right-hand side. Mu squared, similarly, is a constant, and so that can come to the front. And then we can see the different components here. So this is the first term we're going to leave, but note the first term is actually the expected value of x squared, because that function of x, which is just a square, is appearing here. The second term is minus 2 mu times this quantity, which we can see up here, is simply mu. So it's minus 2 mu times mu, minus 2 mu squared. And the third quantity, this sum, by the properties of the random variable, the sum of the probabilities is 1, so that's plus mu squared. So we have minus 2 mu squared plus mu squared leaves us with minus mu squared. So here we have another representation of the variance. So here, the expected value of the square x minus mu squared, and here we can see that's equal to the expected value of the square of x minus mu squared. Now this representation is usually much easier to compute, but just a little warning here. This quantity here, you're taking the expected value of squared quantities, okay? A squared quantity is always positive, or at least non-negative, and so this has got to be positive. You can't have a negative answer. It's very clear in that representation that this variance has to be positive. If you ever end up with an answer using this calculation, which is negative, then you've made a mistake, and you go back and fix it. It's obviously a mistake if you end up with a negative answer. Okay, so let's just do a little example, and we'll return to our previous example just to compute the variance. So the previous example, we had x taking values 1, 2, and 4. We had probabilities of x, half, a quarter, a quarter. We had x times, so just multiplying the first two columns together, half, half, 1. And now we're going to take the product of x squared with the probability. So again, if you write it in this way, which is a very useful thing to lay it out, all we're doing now is multiplying this column by the first column. So 1 times a half is a half, 2 times a half is 1, and 4 times 1 is 4. So we add those up, we get 5.5. And so the expected value of x squared is 5.5. Mu, which we computed before, was 2. That was just the sum of this column. And so the variance of x, using the simpler formula we had last time, is 5.5 minus 4 is 1.5. And so we can think about this in sort of interpretation of the amount of variation that the random variable has amongst its different values. And we could, in the usual way, take a square root of this quantity to think about the standard deviation of the random variable as well. And so I'm not going to talk about standard deviations. Just to wrap up this section, let's just write down a couple of other results, which I'm not going to go into the details for, but you should be able to verify from the definition. So this is, if you like, an exercise. So using the definition of the expected value of g of x, it can be verified. And as I say, you can try this for yourselves, little exercise. The expected value of a linear function of the random variable, and you can see this just by plugging it all in. Simplifying is the same linear combination of the expectation. And this would hold for constants, not random variables, but constants, numbers a and b. And in a similar way, a bit more complicated, it will require rather more lines of calculation, the variance of a linear function of the random variable x is a squared times the variance of the original value for x. Okay, so that's The first one here is probably no surprise that you just end up with the same thing, and that follows through very quickly. The second one, of course, requires a bit more work. You have to take off the mean of this thing and work in the same way as before, and you can see the a squared coming out very quickly.